interest lies in the field of humanoid robotics, motion planning, leg and hand exoskeletons, intelligent control systems, and brain-computer interface for rehabilitation robotics. He has been member of various government sections and industries, including in the Scientific Advisory Board for ISRO Chandrayaan-2 lunar mission in 2009. I would like to mention that he is also a member of the Board of Studies at Center for Advanced Studies. He is also a continuous visitor at our institute, that is Center for Advanced Studies. Here I call upon Professor Ashish Datta to please give his talk. Professor sir.
Yeah, thank you, Dr. Chitra. I'm audible, right?
Yes, sir.
Okay, so I'll just share the screen. You can see my screen?
Yes, sir.
Yes.
Okay, so let us get started. Okay, so as I have been introduced, I'm Ashish Datta from IIT Kanpur, and I'm in the Department of Mechanical Engineering, and also the coordinator and head of Center for Mechatronics at IIT Kanpur. So today I'll be talking about biped robots, and the talk is a little general in the beginning, and then maybe I will, towards the end, I will talk about some research issues in biped locomotion. What are the challenges? What are the problems faced, etc. Okay, so essentially biped robots are, or biped locomotion. When we say, what do we mean by locomotion? So locomotion essentially means moving from one point to another. That is what we mean by locomotion. And we can have locomotion by biped robots. You can have locomotion in air. You can have, for example, birds can fly. That's kind of locomotion. Fishes can swim. They're all parts of what we say locomotion. And the early robots, as you can see, are basically stationary arms, and they were not moving around. Today, industrial robots also do not move around. Okay, and when people wanted to increase the work volume of the robots, they basically tried to mount robots on mobile bases, and then the robot on a mobile base would move around, and we had mobile robots with the arm on top. Okay, and this is the early robotics, 1960s, 70s. Now, the first attempts were made on the wheeled robots, wheeled vehicles. Then attempts were made to increase the work volume in case of. So the earlier robots were all wheeled robots. Okay, that we all know. Now, why wheeled robots? Why not legged robots? Is something that's interesting. Is because wheels do not need any kind of balancing, and they require much lesser energy to move from one place to another. Okay, so the two requirements of balancing and less energy is what made wheel robots very, very popular in the early days. Okay, and wheel robots can be of two kinds, basically holonomic and non-holonomic. Now, non-holonomic system is one in which the degrees of freedom are not independent. For example, a car that you know, a car, four-wheel car that we use on the roads or buses, they cannot move sideways. They can only go forward, and they can turn at some angle. Okay, so such systems are non-holonomic. And on the other side, we have holonomic systems in which the degrees of freedom are independent. For example, cars that can move in any direction. Okay, so such robots are holonomic. This is an example of a holonomic robot which can move in any direction. Now, how does this robot basically work? Is they have wheels, and on the wheel, say this is a wheel, and on the wheel we have rollers which are mounted. So these are rollers which are mounted on the wheel. Now, what happens if the wheel rotates? What would happen is, because the rollers have an angle to the main axis of the wheel, the resultant velocity will be at a particular angle. Okay, so what we can see here is that if this wheel rotates, the resultant velocity will be in this direction. Okay, and there are four wheels, and by suitably rotating, giving velocities to the wheels, we can get a resultant velocity in a particular direction. Okay, now by using this wheel called Magnum wheels, we could have mobile robots that can move in any direction. For example, if you look at this robot here, it can, if all the wheels are moving in the forward direction, in the same direction, then the robot will move forward. If all the wheels are rotating in the reverse direction, this will move backward. Okay, if two of the wheels are rotating opposite to each other, like you can see here, they're rotating. This is this side, this is this side, whereas the other wheels are that side and this side. The resultant velocity will be in this direction. So this is essentially to show that by combining different velocities, you can make the vehicle move in different directions. And this is an example of a holonomic robot. Now, before we go to legged robots, I just wanted to give a very brief introduction of wheeled robots. So wheels are of different types and they serve different purposes. For example, this is a tracked wheel. And this one is essentially a wheel which can, by which the vehicle can climb stairs or it can also move. Okay. Now this is example of other wheels. Now this wheel can be used like legs. It can also be used like wheels. So there has been a gradual change from wheeled vehicles to legged vehicles. You can see this is a wheel and this is a leg, and also a cross kind of vehicle in which you can have, this is a cross wheel and leg vehicle, and which is basically called the athlete rover, which was made for space exploration. And this has legs. You can see the legs here. It has 6 legs. And at the base of the legs, there are wheels. Now, if you're wondering why to have legs and wheels, essentially it is the same answer that wheels require much lesser energy. Okay, so when it is going on flat ground, the wheels will be rotating and the vehicle will go in some direction. But if it is coming to uneven ground like this, it has to go over an obstacle or it has to go over a ditch, then essentially the legs will come into picture and then the vehicle can go over the obstacle. So this is a hybrid kind of a vehicle where you have legs and wheels working together. Okay. Now, something very interesting is that biology prefers legs. Okay, all biological entities have either legs, wings, tails for locomotion. You'll never find a biological entity, either an insect or an animal, okay, which has wheels. So biology prefers legs, although legs require more energy and you require balancing, etc., etc. Okay. Now, one of the reasons for that being that we biological entities have to do different tasks. For example, we have to run, we have to walk, we have to climb, we have to sleep. Okay, we have to sit down, we have to stand up. With wheels, you can't do so many things. So although legs take more energy, but biology always prefers legs because of which all biological entities are having legs. Okay. Advantages of legs: we can walk over obstacles. It has less footprint area. The body can be maintained at a particular height, and it can perform different functions: climbing stairs, sitting down, lying down, etc. So the last one is the reason why biology prefers legs rather than wheels, although wheels take less energy. Now, when we come to the concept of legged locomotion, the first thing that we have to talk about is balance. We said that a wheeled vehicle does not need to be balanced. Okay, now what is this balance? Now, you know that there are two kinds of balance, two kinds of systems. One is what we call static balance or dynamic balance. Now, static is if the system is not moving fast or it's a static system and it is balanced. Okay. Now, dynamic is for a system which is having acceleration, velocity, and it is moving. Now, such a system also has to be balanced. For example, this example shows the case of the earliest one-legged robot. This was made at MIT in about 1980s. It was called the one-legged jumper, and it has one leg, okay, just one leg, and it has a body here. You can see the body, and there is a spring here from which it gets its energy. And this is the one-legged robot, the earliest robot, one-legged, which was made essentially for jumping. Now, some things you should notice here very carefully is that it has 2 degrees of freedom. One is that it can get compressed here. So there is a linear kind of a degree of freedom here, and there is a rotating joint here. Okay. So they are actually basically 2 degrees of freedom. Controlling these 2 degrees of freedom, you can make the robot go front, back, or jump in one place. Okay. So this is the earliest one-legged jumping robot that was made at MIT. And from the physics point of view, okay. So from the physics point of view, basically what I'm trying to explain here is this concept of dynamic balance. Now, if you look at this system here, it can actuate a joint here, or it can actuate a joint, the linear translation joint here, and it can move. Okay, either it can jump in one place or it can go this side or this side, but it cannot stand in one place quietly. Okay, now if I want this robot to just stand there and not move, it's not possible. Why? Because this is a dynamically unbalanced system now. Okay, this robot cannot stand in one place. The moment you want it to stop and stand, it will immediately fall. Now, this is the meaning of balance of a system, and which is very clearly shown from this figure. Okay, a lot of animations have been made of this, and a lot of cartoon characters. For example, this jumping kangaroo. This is a 2-legged jumping robot, exactly the same, and this is a 4-legged jumping robot. Now, in legged locomotion, essentially we have different states through which the locomotion goes through. For example, we saw here that you can have the leg, which is in air, is going upward, the leg is coming downward, it makes contact, the spring gets compressed, and then the leg goes backward again. So these are different states of the system, and we call this a finite state machine, essentially. So the controller that we're trying to develop for this kind of system needs to goes across different states. So for example, this is the flight state, this is the loading state, heel contact state, heel and toe state, toe contact, unloading state, and then flight state. So essentially it means the leg is in air, it is coming down, loading means the spring is getting loaded, it is compressing, then the spring pushes back upward, there is toe contact, and then it goes into unloading, it goes off into the air again. So a control system which is basically working on different states like this is called a finite state machine. And the earliest controllers for such robots were finite state machines. And it had different kind of states, basically from one state into another state. And what are we controlling? In this, basically, we saw that there is one actuator here, which is controlling the body angle. Okay, so this is my theta, then I'm controlling the body angle here. Okay, so this is one controller, which is controlling the body angle. We can put a simple PD controller and control the body angle like this, which is shown here. And another controller, which is controlling the length of the leg. So there's a spring here. So depending on this L, we have to control the L as well as the body angle there to make this robot go forward, backward, or jump in one space. And both of these actuators are controlled by simple PD controllers. But something to note here is that it cannot stand in one place. The moment you want it to stand, it is going to fall. Now let us move from one leg to more number of legs and then come back to two legs again. Now for more number of legs, it's very interesting that if you have four legs, there are different ways by which you can connect these four legs. So these four legs are connected sideways like this, and the body moves this side. Now in this case, the legs are connected like this, and the body moves on this side. Okay. Now this is the case of a mammal. In the mammal, for example, a dog, the legs are connected like this, and in the case of a reptile, they're in the side. Okay. So although we have four legs, all the leg connections are different. Now you might wonder why it is like that. Now essentially it is like this. And now let's look at this example here, which makes it clear. For example, this is the case of a human being. We have legs which are like this. This is the case of a reptile. This is the case of an insect. Okay. Both of these are two-legged, or sorry, not two-legged, they're multi-legged. But essentially, if you try to answer the question that why is the leg connection made in a particular way, then for the human being, if you see, we spend a lot of time standing. Okay, dogs spend time standing, horses spend time standing. So if you look at this, the physical structure here, if we are standing, the weight of the body will go down like this. This is mg coming down, and each of the legs will carry mg by 2 forces, right? And this will mean that the force of the body to keep the body standing, the force will go straight through this leg and onto the ground. The force will go straight from here and onto the ground. There is no resultant moment here. Okay, so in that sense, it requires less energy. Whereas if you look at this structure, the legs are on the side. So it will basically mean that to keep this weight here, what will happen, there will have to be a moment out here. So this will be a moment into this distance. So there is a force here into the moment, will be a moment that will have to be supported by the actuator here to keep this body in that position. So for a human being to have legs like this is a bad idea. Or for a dog to have legs like this, because it will require more energy. But for a reptile, it's a good idea to have a leg like this. Why? Because the lizards or something that crawls on the walls, they have to keep their body very close to the wall, so that the resultant moment again that it has to support here will be very, very low. So when a lizard is climbing on the wall, it has to stick to the wall. Otherwise, it will have to support a very heavy load, okay, heavy torque, I mean. So because of which the legs of the lizard are like this. Now, in the case of insects, the legs are like this, okay? In the case of a cockroach, okay, why is it like this? Now, essentially, again, because for the case of a cockroach, the body is maintained very close to the ground, okay? So the cockroach can, in active, and when it is sleeping, for example, the cockroach can just lie down here and sleep. And this leg gives a very high torque. So the cockroach can run very fast in a particular direction or change its direction, because this kind of a leg structure enables it. So what I'm trying to say here is that we can have 2 legs, 4 legs, multi-legs. But in terms of evolution, we have been given legs of a particular type, particular number, and a particular shape. And there is a reason for it. Essentially, it is survival and energy requirements. Okay, this is the case for an insect. Now let's move on to talk more about. So this is 4-legged, which you would have seen on YouTube. So this is the uh, the YouTube dog, YouTube big dog made by Boston Dynamics. Now, if you look at the structure of the legs, okay, it has a particular structure. Okay, it has 4 legs, but it has a particular leg structure. The legs are folded backwards. If you see very carefully, the leg folding is like this. It is not. It is like this, and this is like this. Okay. Now, in terms of dynamic balance, if you see when it is walking, 2 legs are in the ground and 2 legs are in the air. When it is walking, that's how it walks. Okay, that's how it is maintaining its dynamic balance. Okay, and it is extremely well balanced system. Now you can see that you can push it and do whatever you want to do, and it doesn't fall. Okay, so it is an extremely well balanced system, and the way it walks is basically it follows a particular gait. Okay, so when we're talking about 4-legged kind of systems like this, what we have noticed is that it has legs, which has particular structure. It has a particular gait. At any time, 2 legs will be in air. So this and this, the diagonal legs will be in air, and these 2 legs will be on ground. Okay, then it will change over. This 2 will come in ground, and those 2 will go in air. That's how the body moves forward. And this is what is called a gait. Okay, so we need to remember a couple of things. First of all, that we need to balance this 2-legged, 4-legged kind of robots, and they have a particular gait. And this gait is called the pattern of foot placement. Now, what the gait essentially does is, if you look at this 4-legged or 6-legged robot, and you look at the top view, then there are 3 legs on the ground. So these are the 3 legs which are on the ground. And the projection of the center of mass is coming onto this triangle. And if this has to be stable, or it has to be balanced, the projection of the center of mass always has to be inside this triangle. Which triangle? The triangle made by the legs on the ground. And this is how dynamic balance is maintained. So when it is walking, it always ensures that the projection of its CG is always inside the foot support polygon, which is made by the legs on the ground. So whether it's a 6-legged or it's a 4-legged or it's even a 2-legged, okay, there is a foot support polygon, and the projection of the center of mass has to be in the foot support polygon. There are different ways of having different kinds of gait. For example, if there are 6 legs, then at one time 3 legs can be in air, 3 legs can be in ground. In the case of 4-legged, for example, this is a 4-legged robot. In the case of 4-legged, we can have, let's look at a 4-legged. So this is a 4-legged. So 4-legged, we can have 2 legs on ground, 2 legs in air. Okay, or we can have 3 legs on ground, 1 leg in air. So it can have different kind of gaits. So in terms of biped locomotion, the first thing we need to talk about is balance. The second thing is what is the gait. Now, in case of biped, obviously, this is the case. In the case of biped, we'll basically have 1 leg on ground, 1 leg in air. Then we have 2 legs on the ground. Then we have 1 leg in air and the other one on the ground in that way. I'll explain as we go along. This is the case of 4-legged. Okay, robot. You can see that it has a particular gait. So there are 4 legs. 1 leg is in air, 3 are on ground. 1 leg is in air, the remaining 3 are on ground, and that's how it moves forward. Okay, so that is how it maintains its balance, that this projection of the center of moment is in the foot support polygon of that robot. Okay, now let's look at how do you model such systems. So we model such systems by putting center of, we have a global frame. So this is my global frame, this is my XY axis. And we have a local frame which is fitted onto the robot itself. Now the robot can be 4-legged, it can be 2-legged also. And this is my global, that's my local. And with respect to the global, each of this is like a robotic arm. Okay, this is a robotic arm. And we can take our transformation matrices and go from here to here for each of the legs. So each of these legs are controlled by using the kinematics and then the dynamics for moving forward. Okay, and this is how we assign our axis. Now, historically speaking, there are some interesting things here. For example, if you look at the earliest walking robots, when people tried to study walking mechanisms, they basically observed that if you have a wheel and you keep a wheel on an inclined surface, the wheel will start rotating, okay, by itself. So you're not giving energy to the wheel to rotate. But this will only happen if it is on an inclined surface, not on a plane surface. Now, why does the wheel rotate on an inclined surface? It's because if you see the projection of the CG, this is my CG and I see the projection, then essentially it is coming out of the contact point. This is the contact point. And because of which there is the resulting moment which is coming about this point. So this distance into this mg is a moment about this point and the wheel is rotating. Okay, so that's why a wheel rotates. So people thought that if we can make a robot like a wheel, now look at this robot, 2-legged, and it has legs. This is the wheel. If I see this, the wheel, these are the spokes of the wheel. Now, if this is designed like a wheel, then this robot should be able to walk down a slope without any energy, without any actuators. That's the best thing that can happen. No energy given, and the robot is walking. So the earliest robots were called self-propelling machines, or passive walkers, in which they were made like the wheel and they could come down inclined slopes. Now let's look at this example here. Okay, so this is a passive walker. Okay, it is made, these are two legs, you can see, and the bottom are made like, is made like a wheel. This is an incline and it can come walking down. Okay, how does it walk down? You can see this again, it is walking down a slope and without any energy. There's no actuator there. And how is it doing? It is essentially, it is behaving just like a wheel. Okay, so if you can visualize, if you look from the side, this will look like a wheel. So the shape of the leg is made something like a wheel. And these were the earliest walkers, which were called passive walkers. Okay, so this is also an example of a passive walker. So there are two legs. This is one leg, although it looks like two, but this is one leg and that is the other leg. And it can walk down an incline without any energy. Where is the energy coming from? The energy is coming from gravitational energy. Okay, so these are interesting, the earliest examples of walking mechanisms and walking robots called passive walkers, which do not require any energy for walking down an incline. Okay, now people studied this in terms of dynamics. This is also another interesting toy, which in our classes here, we ask the students to make this one just to understand dynamics, just to understand how the dynamic system is working. So you can look at the two legs. It is like a wheel if you see from the side, and it is cut like the in the shape of a wheel. And these are two weights which are moving from side to side, and the two legs move it forward. So this is called a passive walking toy. No energy, it can walk down a slope, okay, by itself. Okay, such systems are called passive walkers. And in terms of dynamics, where is the energy coming from? It is coming from gravitational energy. Why is it walking down? Essentially because the design is something like a wheel, and a wheel comes down. So if I can make the leg design like this, okay, if you can imagine, and if I cut it here and I cut it here, then this is one leg, this is another leg, but this is like a part of a wheel, and the wheel comes down. So on an inclined surface, this will come down also. So this was the earliest kind of walkers called passive walkers. Passive walkers means no energy requirement. They walk by gravitational energy. Now, moving forward, we have dynamic walkers, a lot of them. Now, these are active systems in which each joint has active degrees of freedom, and they can move up a slope, down a slope, 3D. In 3D, they can walk in different kinds of terrain, and they are complex systems. So a lot of bipeds have been made. For example, this is very famous, the Azimuth system. Incidentally, this is the first one proposed 1921 by Karl Kapek, and from which the word robot actually came. So the robot came from this, where he said that in future, there'll be mechanical men who will replace human beings. And that is where he used the word robot. And this is 1921. This is about 1998. We have a lot of more of them, one here, and lots of them. So let's very brief, and this is probably the best one that has been built as of today by the same group of people who built the big dog. So this is Atlas, and it is able to walk. It's a biped, which has two legs, hands. It has a vision system. It has LiDARs, cameras, and it can walk on any kind of terrain. Okay, now this is of course the only one in the world, and it is extremely complex. Okay, but the basic concept of balance, the basic concept of dynamics is the same. Okay, so that is something we'll be looking at. So in terms of balance, you can have a look at this is something interesting. Okay, just this part quickly we can have a look. Is that the robot needs to be balanced, and if it falls down, it should also be able to get up by itself. Okay, so it has fallen down, and it should be able to get up by itself. Now, for a human being, it's very easy. We know how to get up, but how does a robot get up? Okay, so there are a lot of challenges in the study of biped locomotion, humanoid robotics, not only in terms of just simply walking, doing tasks, going into three-dimensional terrain, getting up, falling down, etc., etc. Now, let's talk a little bit more into the theoretical aspects and try to understand when we say walking mechanism, bipedal walking, what is this walking and how do we enforce it? So this is a walking, this is the basic understanding of walking. When we say walking, what does it mean? This is a human being, you or me or all of us, okay? Our walk can be divided into two planes, which means if I see from the front, when you are walking, if I look at you from the front, then I can see you're in the frontal plane. So this is my frontal plane, means I'm looking at you from the front side. Okay, so your gait or how these legs are moving will be projected onto the frontal plane, and that is my front view. I can look from the side. Now, if I see from the side how these legs are moving, from the side, if I see, they are projected onto the sagittal plane or the side plane. Okay, so essentially walking is on two planes, the lateral plane, sagittal plane, and the frontal plane. Okay. Now we walk essentially on these two planes, and I'll just briefly go here and see if you're looking at this robot chair, okay, which is a two-legged robot which is walking. So this is a two-legged robot which is walking. Now I'm looking at the front plane. So this is the frontal view. So this robot is walking, and when it is walking, it is moving from side to side. This is something that you observed here, is that this robot is walking from or moving from side to side. So if I look at you or you look at me from the front, or you look at anybody from the front side, the person will move from side to side, okay? And that is essentially to maintain dynamic balance. Okay, now, why is it moving from side? Essentially, the projection of the center of mass has to come on the foot on the ground. Otherwise, it is dynamically unbalanced. The person will fall, okay? So whenever you're trying to lift your, move forward, you'll first move on one side, then you will then what we are going to do is we are going to move on from one side to the other side. Okay, so this is the idea of dynamic balancing. Okay, now if you look from the side plane, then what do we see is we see this. Okay, so that is from the front view, and this is from the side view. Now this is from the side in the sagittal plane. What you're seeing is when the leg is going up, the center of mass has to be on the foot on the ground. So by combining the front view and the side view, the body essentially moves forward. Okay. So what I wanted to show essentially here is that when we are walking on two planes, front plane and side plane, and dynamically we have to balance the system such that the body is balanced, which means the projection of the center of mass has to be on the leg on the ground. Okay. Otherwise, it will fall. So the most essential thing in the biped locomotion is balancing. And how do we enforce it? We enforce it by doing the kinematics in such a way that the projection of the center of mass is on the foot on the ground. Okay, that's how we ensure balance. Now, how does the body move forward? So if this is the leg on the ground, this is the front, and this is the rear leg. If you can imagine yourself, this is your leg at the back, this is the foot on the ground. Then your rear leg will move forward like this, and the hip will move forward like this. The body also moves forward, and the whole body has come forward now. So when we are walking, we walk in two phases. The first is we move the body sideways, rear foot, and move it forward, and move the hip forward, by which the full body comes forward. So there are two basic kinematics which has to be carried out. One is the body has to move on one side, and then the rear leg has to become the front leg. Okay, and how do we ensure balance? Now, balance is essentially ensured by if you look at a dynamic system like this. Okay, so this is a two-legged robot. It has a body also. This is the leg on the ground. So the leg on the ground essentially means that, or if you look at all the links, these are the point masses. So each of the links are represented as a point mass, these black fellows. Okay, and if this is a point mass, this point mass is subjected to two forces. One force is the gravity which is pulling down, which is mg in this side. Okay, so this point mass, all will have mg acting in this downward direction because of gravity. Now, this is a dynamic system, it is moving. So what will happen? It will also be subjected to accelerations in the direction in which it is moving. So if acceleration is A, then mass into acceleration is the force in this direction. So each of these masses are subjected to two forces. One is a gravitational mg, and the other is the acceleration force, which is mass into acceleration because of inertia. Okay, so each of this is subjected to two forces, and if we take the sum of all of them, all the forces, then what will happen is there are forces in this direction, there are forces in all other directions. If I sum it, all of them, then the resultant force is going to act at the ankle here. Okay, now the ankle will have a force, the resultant of all of those forces, which is going to act downward, okay, because the forces are acting downward now. It is on the ground, and this force acting downward will be balanced by a reaction from the ground, which is upward. So the forces which are acting downward, forces which are acting upward are always balanced. So forces do not cause a disbalance. Now, this force will, the forces acting on this body will also cause a moment about this point. Why? Because there is a force like this, and there is a distance there. So there is a force into distance, a moment which is coming here now. So these fellows will also cause a moment about the ankle joint or the foot on the ground. Okay. Now, for balance, the forces are always balanced. Why? Because of Newton's third law, forces in this direction is equal to forces in this direction, forces, no problem. but there is a moment which is acting. Now, unless that moment becomes zero, what will happen? This will fall in that particular direction. So in order to balance a walking robot, we have to ensure that that point, which is called the zero moment point, is on the foot on the ground. Now, how do we compute that? We basically compute the forces, so mg and ma, sum of that, plus the moments, the forces in this, into that distance is the moment. So I compute forces, sum of forces like this, gravitational force minus acceleration force, and moments, which is the distance between the force, line of action of the force and the ankle joint, and have sigma of this and sigma of this. Forces are balanced, so there's no problem, but the moments are not balanced. So which means that I need to have a point. So if I look at this figure here again, if there is a force acting like this, so I need to have a point in which about this point, the force into the distance, the moment that is being created, will counterbalance all the moments which are created by all these other joints now. Okay, so if such a point exists, then that point is called the zero moment point. And this is how we find our zero moment point. Essentially, if there is a point about which the resultant forces into the distance is equal to the sum of the moments which are acting. If such a point exists and it's on the foot on the ground, then we say system is balanced, and we can find this point by using this, computing it this way. Okay, which is not very difficult once you understand what is happening here. Okay, so it is very interesting here again, and I keep coming back to biological systems because we are talking of biological robots, but we are human beings. We are also bipedal, and we are also walking using exactly the same principles. Okay, you may not believe it, but please believe me when I'm saying that we also have to satisfy the zero moment point. So when we are walking, if you look at the sole of your foot, okay, the zero moment point starts from here on the heel of the foot. So when I take my leg forward, what we do is we make contact at the heel point first. When you walk, please observe the next time. So when you take your rear leg forward, you make contact at the heel, and then the zero moment point starts from here. Then it goes like this, goes to the toe, and then goes to the other foot. Okay, so in our foot also, basically the zero moment point has to be satisfied because we have to be balanced when we are walking, and it starts from here, goes like this, like this, like this, goes to the big toe, and it goes up to the other foot. The other foot means the foot on the ground. Okay, so if this is the foot on the ground, the other foot is the leg on the air. Okay, then it will come to two leg. Okay, both leg are on the ground, and then it will be the other leg on the ground, and this leg is going to be on air. So alternately, the zero moment point stays on the leg on the ground, and then it goes to the other foot, leg on the ground, and moves like that. What's interesting here is that the zero moment point moves from here like this, and then goes off. Now, what's interesting here is that the zero moment point does not go here. It does not go there. So actually, this has no function on the legs, because of which all our these small toes or the small fingers are very, very small. They don't have any function. They don't support the zero moment point. Zero moment point is only supported by this, and that. Even on this side of the foot, okay, you see there is an arch there, and it doesn't do anything. Okay, and if you look when you're walking, if you look at your shoes, if you have never noticed your shoes, please look at the bottom side, the sole of your shoes. You'll always find that it gets worn off this side. Okay, the shoes wear here, the shoes never get worn there. Okay, why? If you're wondering, please come back to this equation and try to understand that when you're walking, what is the dynamics which is going on, and the robot has to satisfy that. Even the human being has to satisfy that. We have to satisfy it. Okay, and that's something interesting here. Okay, let's move on. Now, we said that the walking gait is essentially in two planes, and we have to make it walk. How do we make it walk? We have to move the robot first on one side so that the zero moment point comes onto this leg. Then the rear leg moves forward, and the whole body goes forward. That's how the whole robot moves forward. Okay, it is balanced and it moves forward. What is the gait like? First, it is on two leg stance. Then it's on one leg stance, then it's on two leg stance, and then it's on one leg stance again. So it is 2-1, 2-1, 2-1. That's the way it alternates, the gait for a biped robot. Okay. Now, the inverse kinematics of this is not very difficult, because those of you who have studied robotics would know that if you have two links and you have 2 points, 1 point here, 1 point here, then essentially there are two solutions only. There is one solution like this, possibilities, and the other one is like this. Okay. So I know this point is leg on the ground. So let me go back here and try and explain this here. So from this figure, if you see, in terms of the kinematics, how does this move? If I say this leg is on the ground, then this leg from here moves like this and comes here. So what I need to do is the ankle joint goes like this, and the hip joint goes like this. And at every point here and every point here, this leg will be having a solution like this or like this. Okay, so we neglect this solution and we take only this solution. So this is a two-link system. So there is only one solution, and I know what the solution is, and I can do very easily using geometry. I don't need to do any complex kinematics. So what we do is I have a spline here, I have a spline here. I divide this into 20 points, and every point has a corresponding point there. I just connect by two links like this, and then I know what are those angles from geometry. Okay, and that's how the robot moves forward. So it's pretty simple actually. And in the side view, and in the front view, what I do is the leg moves on the side such that the CG comes onto this leg, and based on which the system is balanced, and then the leg comes forward. So there are two phases. First, you go sideways, then the leg goes forward. Now, again, you would know that I can have any trajectory here. I can have infinite trajectories. So there can be different curves. The leg can go up in infinite ways. So there has to be some kind of optimization by saying that what is the optimal trajectory? Okay, because it is possible to walk in infinite ways. So we have to optimize the trajectory, and what we do for optimizing, we have to find out the torques acting, okay, for which we can use standard dynamics, we can use Euler-Lagrangian, or we can use Newton-Euler methods. So when the robot is moving forward, what we can do is we can find the torques at the joints, and from the torques of the joints, I can find the equation of motion. Okay, and the equation of motion comes out something like this, which is the torque at the joint. This is the inertia forces, this Coriolis centrifugal force, and this gravity force. Okay, so using this, we can find out when the robot is walking, what are the basic, what is the energy consumed for a particular trajectory. And for optimizing, what we do is we try and find or we try and fit infinite trajectories. So when the robot is walking, I take one trajectory like this, one like this, one like this, and for each of those trajectories, I find what is the minimum energy, what is the energy, and then I compare all the energies and say that for this trajectory, the energy is the minimum. So that is basic optimization. And we can do optimization by fitting splines or polynomials onto the trajectory, and by using methods like genetic algorithms or any other optimization method. So what this basically does is it fits different trajectories and then finds out the energy using dynamic equation, and then says for this trajectory, the energy is the minimum. So it's the best trajectory. Okay. Now, what is the optimization function? Is basically energy. So energy is torque into the velocity into the time. Okay, so this is work done, this force into distance moved, okay, into the time, which is energy. So my objective function is integral of tau d theta dt. This is the velocity, and this is the time. Okay, so so by optimizing the work done, we can find out what is the minimum energy trajectory. Okay, so this is the optimization procedure that is followed. This is used for finding the dynamics, finding the torques at the joints. This is the work done, the cost function, and for fitting different trajectories, we can find what is the basic, which trajectory gives the minimum. Something interesting here again. Again, I come back to biological systems. So when we walk, we have in our legs, we have 8 degrees of freedom. So 8 plus 8 is 16 degrees of freedom. So in our legs, we have 16 degrees of freedom. So if you have 16 degrees of freedom, you can have infinite solutions, okay, because it is a hyper-redundant system. The degrees of freedom are much, much more than what is required to walk, okay, which means that you will get infinite solutions. Now, what this means is that we can walk in infinite ways, which you know, that we can walk in different ways. What I mean is our leg trajectories can be infinite, which means that all of us should walk in different ways, because we have infinite degrees of freedom in our legs. Okay, but it doesn't happen like that. That when you look at human beings walking, we more or less have the same trajectory of walking. Please observe your friends when they walk. You'll find that their trajectories are same. Okay, and that is very interesting. And the trajectory is something like this. Just call an inverted S. So if the rear leg goes up, then it comes down like this, then remains flat to the ground, and then comes to stop here. Okay, and we can prove by optimization that this is the optimal trajectory of walk. So which means that biological systems are also optimized, and we walk in such a way that our trajectories are optimized, and because of which all of us have the same trajectory when we walk. And this is something interesting. Okay, and it has also been proved that they are optimal trajectories. Again, when we are going over an obstacle, there is an obstacle here. I want to go over it. My trajectory will be something like this. If I'm climbing stairs, my trajectory will be like this. And we all do it in the same way. And it has been proved that these are optimal trajectories in terms of energy. So biological systems are actually optimizing energy. We are maintaining balance and we are optimizing energy. So when we are trying to design a robot, the robot should also be doing almost in the same way, right? Now, Uh, this is the very basics of biped locomotion: balance, dynamics, trajectory generation to make it walk. Now, in terms of research, what is new? In terms of research, people have talked about adding compliance to systems. For example, you would notice that the soles of our feet are soft. Okay, in fact, all our joints are soft. So, and when we wear shoes, the sole of the shoe is also soft. So, is there some reason for that? Okay, why is the sole of our feet soft? One reason is we can absorb shocks, shock loading. So, otherwise, when you're walking or when you're running, if it's a very rigid leg, what will happen? You'll be getting impact loading, okay, which is going to be very, very harmful. So in the case of if we add a very soft kind of a sole to a biped robot, we try to see what happens then. And so the idea came from human sole and from our shoes. And what we see essentially here is if I put a soft material under the legs of a biped robot, then what happens is when it is bending on one side, this soft material is going to deform. Now, if it deforms, now this deformation basically means that it's a passive system. This is passive. So it is taking energy and is giving back energy. It's like a passive string. Okay. So which means if you put soft material in there, it should have an effect on dynamics now. And if you study the dynamics, what we were able to see and we were able to find is that if you have a robot which has, if you put a soft material and then do the dynamics, what we find is that it takes less energy. Okay. It can absorb shock and it takes less energy. Now, this is now, of course, it is going to depend on the material also. If you put very soft material, what will happen? It'll keep vibrating. Okay, when it's trying to walk, it will become unstable if the material is too soft. So there is some optimal material stiffness which has to be put under the foot, which will make the robot stable, and you're going to save energy. So this is a robot which we had made many years ago, in which we were able to show that if you put this soft material under the sole of a foot, the optimal trajectory will be like this, and it is going to save energy. Okay, and that is probably the reason again why we have. So this is a robot which we had made a long time ago with soft material. So when it walks, we were able to show that it saves energy. So a lot of things in biological systems like soft energy, soft sole, they have a particular reason. And from dynamics, it shows that. Now the next is the effect of muscles and tendons. So in our legs, we have soft sole, which I just showed. Now you also have muscles and you have tendons. Now these tendons tend to behave like springs. Okay, they tend to behave like passive springs in our legs, in our hands. So we have a muscle, and then we have a spring. We have a tendon which is connected to the joint. So the muscle contracts, the tendon is pulled, and the joint moves. Okay, but this one has some kind of spring-like behavior. And if you make a robot and try and incorporate that behavior in the form of a torsion spring, we tried to see what happens then. And again, we were able to show that it actually takes less energy. You save dynamics, you save energy. So we made a robot in which we put the springs in the joint. So we have an actuator, then we have a spring, and then we have the joint. Okay. And our dynamics equation, the only difference that will happen now is that we'll have a spring constant coming in here. So this is inertia forces, Coriolis centrifugal force, this is gravity force, and then we have the spring force, which is coming in here, F is equal to kx, which is my spring force. So the dynamic equation just gets modified. But our work done is exactly the same as before. It's the torque into the distance into time is the work done. So if I optimize it and I see something interesting that we found here is that for different spring stiffnesses, we were getting different gates, okay, which is maybe understandable. That if you change your spring stiffness, your optimal gate or your optimal trajectory will change. And this is showing us that different trajectories, optimal trajectories, if you change your spring constant. Now, something more interesting there is that there is something like an optimal spring constant. Now, this is showing that if you have different optimal spring constants, so this is my stiffness of the spring, and this is the work done, then what we find is that if your stiffness is somewhere here, then the work done is minimum, which basically means that if you're putting a torsion spring at a joint of a walking robot and trying to save energy, then it must have some kind of an optimal stiffness also. You cannot put any stiffness. Okay, and this is an interesting result that you can make a robot save energy by putting an optimal. But from mechanical engineering or from engineering point of view, it is more interesting is that if you make a spring and put a particular stiffness, you cannot change the stiffness, right? Spring has a particular stiffness. Whereas in the biological system here, we are able to actively change our stiffness. Okay, so that is the superiority of our biological systems. That we have stiffness, yes, this behaves like a like a spring, like a linear spring. But then we are able to automatically change the stiffness of the spring and put whatever stiffness I want. For example, when I'm running, when I'm jumping, I can continuously change this one. But in the case of a robot, the moment I put a particular optimal stiffness and I cannot change it, then it is only for that gate, nothing else. Okay, so this is again superiority of biological systems over. A lot of people are working in robotics in this area, how to make optimal stiffness devices, optimal stiffness robots, arm robots as well as legged robots. Okay, so this is a research issue even today, and mainly so because a lot of industrial robots, they want to make them safe. They want to make robot-human interaction, robot-human cooperation. One way of doing that is to put springs or make the joint soft, such that if the robot hits something, it absorbs the shock. And how can you do that? You have to put a spring in the joint. If you put a spring and you put a fixed stiffness, then it is only for that particular force. So you must have a robot which has a spring, and it should have a variable stiffness now. How do you make variable stiffness? That's a challenge. It's extremely difficult to do that mechanically. Okay, and so this is a challenge of making robots with variable stiffness kind of joints. Some other work which we had done, I'll just go through some of this very quickly because I think I'm going out of time. So the other is we have talked about joints which are having stiffness. What happens if you make the links of biped robots to be soft or to be compliant? For example, this is a rigid link robot. Okay, it's a biped robot rigid link. Now, suppose I take off this rigid link here and I put a compliant link here. Okay, compliant link means I put a C-section, for example, this one. So I've removed this rigid link and I've put a C-section there. Now this C-section behaves like a torsion spring. Okay, so this is a C-section which is going to behave like a spring now. So when it is walking, this fellow will start behaving like a spring. It'll deform and then it's going to behave like a spring. So what happens then? Two questions come in here. Well, not only two questions, multiple questions. What should be the stiffness of the spring? What should be the shape of the spring? What should be the material of the spring? All these questions come up. And we tried to study the effect of different shapes of the spring, and we found that this is the shape that gives the minimum, it gives the maximum deflection. So this is a robot which we made, in which we made the knee joint by using a C-section. Then we did a finite element analysis to find the deflections of the spring. So this is the FEM model, and then we were able to model the robot with a spring. So this is a compliant link robot. The robot has a compliant knee joint, and it can walk up a slope, it can come down a slope, it can walk on the flat ground. But we observed a couple of things. The first thing that we observed is that if you look at the zero moment point, this is the rigid line is for the so the rigid link is for the rigid link robot, and the robot which is having compliant link, we're here. Okay, and the robot which is having the compliant link is having a little different zero moment point. Now, why? If you look at this video, it becomes very clear that. Let's look at this video. So this is a robot. You can see two-legged robot. It has a C-section here, so it is compliant. So when it is walking, it's a dynamic system. But because it is compliant, what has happened? This will start deflecting. It behaves like a passive spring. And when it is walking, what is happening? It is saving energy. It can absorb load. For example, if it is jumping or running, it can absorb that kind of shock load. But when it is walking, a lot of vibration is coming, that you can see in the video. Now, why this is happening? Essentially because there is a passive spring in there, and that is behaving like a spring. It takes energy, it gives back energy, so the whole system starts vibrating. So it has advantages, but it also has disadvantages. Okay, so we can make robots using passive joints. We can make robots using passive links, but they again lead to a problem of variable stiffness. Okay, and there are vibrations, and it can make the system unstable. So if you try to make this robot walk very fast, it tends to fall down. So this is an example of a robot which with a compliant joint. So what I'm trying to do, essentially, I talked about robots, basic biped locomotion, the type of legs, how many legs, the shape of legs. Then what we try to talk about is basic biped locomotion. How does the body move forward? What is the kinematics? And why there are infinite solutions? Now, from infinite solutions, you're supposed to choose optimal solutions. How do you choose optimal solutions? That also I did explain. And in terms of research, what is the directions of research in this kind of robotics applications? Is number one is to have compliant joints. Okay, I have variable actuator joints, variable stiffness joints. Then to have link structures which are variable, etc. The other area of research, which I will just cover up very quickly, is in motion planning. So we have robots, okay, which can go from one place to another place, biped robots or full body humanoid robots. But now if the robot has to go from one place to another place, like for example, it is going from here to here, and there is a ditch in between, or there is three-dimensional terrain. Three-dimension, I mean, it has all kinds of shapes. Then this is another problem in motion planning, which is in terms of research, which has attracted a lot of attention, and a lot of people are working on this now. Motion planning of bipedal systems to go from one place to another place, maybe avoiding a ditch or so. So how do we solve this problem? Very briefly, is essentially we look at some motion planning algorithms. That means I'm here, I want to go here. So I have to find a path that will take me from here to here, taking the minimum energy. Minimum energy, how? We know how to find minimum energy. All I need to do is to do the dynamic equations, find the, for example, if it's going like this, or it is going like this, or it is going like this. Then when it is going along this path, I can find out from the dynamics what is the energy it is taking, and then find for which one it is going to take the minimum energy. Okay, and then I'll say that is my minimum energy path. And so doing that, what we can do is we can also find the minimum energy path to take it from one point to another point. Okay, so this is where a lot of people are working on in motion planning of biped locomotion. And one way of solving it is by using what we call the wavefront propagation. So wavefront propagation is something like the way waves propagate on a medium. Okay, for example, you would have seen in a lake, or a very placid lake. Okay, if you drop a stone, say this is a lake, this is the surface of the lake, and I drop a stone there, what will happen? Waves will be formed, and these waves will be moving in particular directions. Okay, now the direction in which there is least resistance, the wave will move fastest in that direction. Okay, so this is an indicator that this is taking minimum energy to go in that direction. Okay, so this is what is called wavefront propagation. And what we do is, if we have a three-dimensional terrain, something like this, three-dimensional surface, then, and there is an obstacle here, okay, or there's a high gradient here. So this wavefront propagation will basically tell us which is the easiest way which will take you from here to here, least energy way, which will take you from one point to another point. So biped locomotion has not only walking, dynamics, it has also these associated issues of how do you go from one point to another point? How do you do a particular task? For example, you want to pick up an object, keep it somewhere. Okay, there are always infinite solutions. So in terms of research, this is a very active field of research. There is a lot of research which is still to be done, but it is also interesting because human beings also do solve problems like this. So this is, I'll just stop with this simulation. So this is a three-dimensional bipedal locomotion to go from one point to another point, avoiding a ditch. So there is a ditch in there. So it has to find out where to cross, and it has to find its path and then go from one point to another point. So with basic kinematics, dynamics, motion planning, we can make biped robots. We can do research in biped robots. And these are some of the issues in biped locomotion that are existing in terms of research. So I think I have finished my time. So I would like to stop here. So thank you for your attention.
Hello, sir. Here's a question from one of the audience.
Okay, so how do we proceed? The next, I'm done. So the next speaker,
Yeah.
or
here's a question.
We are not taking questions, right?
Yeah, here's a question with from one of the audience. Here I put it. The question is, how can a robot balance itself in air where there is no ground contact, and also the robot is not having any wings like an airplane or a helicopter does have wings? So how does a robot balances itself in air where there is no ground contact and the robot is
Hello.
having wings? So this is the question. Are you able to hear me, sir? Professor, sir?
Okay, so there is a question here. So you can hear me, right?
Yes.
Yes.
Okay, so there is a question. I'll just read it out, that how the task of balancing can be done in air if robots are not using any wings like aeroplane or helicopter, and when there is no ground contact.
Yes.
Yeah, that's an interesting question. And for that, I have to go back to one of the slides. Okay. in which we said that we talked about balance and we talked about the zero moment point. Okay, so we talked about the zero moment point. That zero moment point is valid only if the foot is in contact with the ground. Okay, now if both the feet are in air, for example, when you're jumping or when you're running, okay, very fast, then the zero moment point is not valid anymore. Okay, so how people have tried to solve it is that just before contact goes from the ground, before the foot leaves contact, then the zero moment point has to be satisfied. And when it is landing again zero moment point has to be satisfied. Now, what it's doing in between, they don't care. Okay, so that is one way people have tried to solve this problem. But you're right in saying that if it is, if both legs are in air, then zero moment point is not valid anymore. And that is another issue of research where people who are working on running robots, they deal with it. That when a robot is running, how do you ensure balance? Okay.
Okay, thank you, sir. Vrinda?
Yes, okay. I will start again. Thank you, Professor Datta. That's
your mic is muted, I think. I can't hear.
Yes, you can hear right now? So, yeah. Hello.
Yes, we are able to hear you, Narendra, sir.
Yes. Thank you, Professor Datta. That's a very interesting talk on robotics. That's I have enjoyed a lot. So it's time for our second speaker to introduce the second speaker. That's Mr. T.S. Rajput. He is currently as a Deputy General Manager at National Small Industries Corporation. He holds numerous positions at NSC in Rajkot, Aligarh, and New Delhi, as well as in Kasipur. He is actively leading the national program for NIC is the implementing as ISO 9000 lead auditor, energy auditor, entrepreneurship, productivity, and project assessment. He's he has also trained in the these quality, cost, and delivery type in the various outside of the country. So he has successfully also assigned completed for various foreign assignment with the different countries like Taiwan, Germany, Canada, Brazil, that is associated with the NSIC, and he is leading the project there. And he has also published the papers on ISO 4000, 14,000, and he also completed one book on this inspection of inspection and quality control. So he is also conducting the over the more than 200 training programs on productivity, cost reduction tools, low cost automation, ISO 9000, manufacturing technology, team building, industries 4.0. So overall, his experience is over 35 years in these industries and small scale industries. So how the government agencies are developing the plans for the entrepreneurship and other things. So he will much more focus on these entrepreneurship development program, how the government agencies are planning and how they are incorporating with the and how they are helping to the students or maybe faculties and as well. Yeah, anyone. So who is developing the any idea and how that can be implemented by this government agency. So I would like to welcome this Mr. T.S. Rajput. Please, you have already shared your slide. Please, please close the screen and then go ahead. Yeah. Please unmute your mic. Your mic is muted. Yeah.
Hello.
Yeah.
Now you are here.
Yes, we
okay.
can hear you.
Okay. Thank you, Narendra. You have introduced me as my name is T.S. Rajput. I am working with NSIC since last 30 years, and 5 years I worked with private organizations like that, ISR and MLVESPA. My today's topic is Entrepreneurship Development Program. As Professor Datta explained everything that is research, how we commercialize the research. So whoever is done the research, that is the need of the country and the world to commercialize it. Mic problem? Hello? नहीं आ रही है? Hello? Hello?
Yes, currently is
Very-
better, I think.
Now you are hearing. Okay. So my topic is entrepreneurship development program. Actually, we motivate to the students of various universities and colleges for entrepreneurship.
Okay, please full screen that one.
Okay. Okay. So the aim and objective of this program is to guide the students for career options and help them to select career boosting ventures or business, to motivate unemployed youths for self-employment, as there is constraint for employment in government jobs as well as private also, to create awareness of NSIC model of incubation for setting up new business enterprises, as NSIC introduced since last 12 years. NSIC model of incubator is very successful in our country as well as abroad. We have supplied more than 20 projects in South African countries and Ethiopia, Indonesia, and this Sri Lanka, Nepal also. So create opportunity for identification of appropriate technology, to create awareness about industry structure before starting business, how they will proceed and which type of industry they want to set up, to promote micro, small and medium enterprises, as NSIC is the government agency to promote it, to enhance the entrepreneurial as well as managerial skill of the participants. So to the topics we will discuss, that is importance of the entrepreneurship, role and characteristics of an entrepreneur, definition of micro, small and medium business enterprise, types of small business entities, process of setting up of enterprise, government approvals needs, requirement of industry, market survey, and question answers. So why entrepreneurship? What is the importance to become entrepreneur? We are seeing, this is the sort of rough survey. Whatever the literacy ratio in India, it is too much now, but accordingly, government jobs are not there. Almost 3 to 5% employees will get government, either state government or central government. And 30 to 40% jobs are lies in private sector. So if we go for together, it is only maximum 45%, but it is less than 50%. That's why more than 55% people are unemployed. Even they are literated. So there is the problem of unemployment, and it is increasing day by day, near about the ratio of 7%. So what is the solution of unemployment? If there is a problem, unemployment is a problem, there are several solutions. That is, main is employment generation. So we can generate the employment by self-employment. If 10% people start their own business, they employ other more 20% people. So 30% people get a job in that respect. Who is an entrepreneur? So we have learned Hindi व्याकरण, कर्ता ने क्रिया के द्वारा कर्म किया. So here entrepreneur is noun, he is individual, he or she maybe, who will start the business to take some financial risk. And entrepreneurship is a verb, it is a process by which method we will start and we will proceed for business. Enterprise is the work. It may be a company, it may be a business house, it may be an organization or a workplace where we perform the work. So if we think, little bit think, okay, why we should go for entrepreneurship or a self-employment? If we want to become rich, to become well-known person, are you willing to help to others, to create opportunity, to become a leader or and do different than others because it is the quality of a leader, to become problem solver or your nation and the whole world? If yes, then you may go for entrepreneur. I think Mr. Dhirubhai Ambani is the great entrepreneur in our country. He has not any background. His father was a school teacher. So he is not having family background of business. So this is a myth that the family people whose family are business person or business woman or businessman, they can do the business. It is not true. So Reliance industry created by Mr. Dhirubhai Ambani, and the slogan of this industry is growth is life. Another, if we see the business persons in India as well as in world, all are rich persons, they are business person. None of one is civil servant, none of one is BC or prime minister or any countries of Rashtradyaksh, any president. If we go Indian, this is change every year, but Mukesh Ambani, since last more than 10 years, he is maintaining first position earning. He is the richest person in our country, and other than these are 10 people's name is there. What Patanjali, who is running by two Babas, Banej, and they are also in 48th numbers. So what are the characteristics it should be in an entrepreneur? Achievement orientation, self-confidence, initiative, willingness to take risk, opportunity seeking, leadership, commitment to honor word, strategic and